All right, so like I have already mentioned, there are exceptions to the octet rule. Um, Obviously, we already talked about hydrogen. Hydrogen only needs 2 electrons to fill its outer shell, so it's happy. It's happy. There are odd electron molecules that do exist, which means the central atom will have fewer atoms than needed. I'm not going to ever give you one that's an odd electron molecule, so that's just a little hint that your number of electrons should always be even. Still, if you forget to subtract and you add instead, then that's another thing. But you shouldn't have an odd number. In the end, there are a few electron deficient atoms. So like I mentioned a little bit earlier, beryllium really is happy enough with only 4 electrons. Beryllium is, you know, it's in the 2s2, and it's kind of happy enough just to make 2 bonds and be done with it. So if you have an element where beryllium's in the center, you only give it 4 electrons, you're fine. Same thing with boron. Boron's happy with only 6 electrons. It's fairly happy. It may react in different ways, but boron compounds are happy with 6 electrons. So usually what happens is it makes 3 bonds, it has 6 electrons, and you don't have to make a double bond to it because it generally is okay with 6. So yeah, these molecules tend to be reactive. However, they're okay with less than 8 electrons. Then there are the other exception is that some molecules, and they only can be elements that are in the, they have to be in the 3rd period or lower down. So phosphorus can do it, sulfur, chlorine, anything further down. So carbon, nitrogen, oxygen, fluorine cannot have more than 8. But if you're in the 3rd row or further down, you can have more than 8. But it's only true if it's the central atom. And so the central atom can actually have up to 12 electrons. So if you end up having any Lewis dot structures that has extra electrons after you've used up all the electrons you think you need, you can put all the extra electrons on the center because the center can have up to 12. It's actually what's happening is because we're in the 3rd row, we have empty d electrons that can help with the bonding. So that's what's happening there. So here's an example. P5, PF5, obviously to make a bond you have to have 5 things bonded to the phosphorus, and since phosphorus is in the 3rd row, it can have up to 12 electrons. So right now it has 10, so it's happy. And if we did the valence electrons here, phosphorus has 5, and then 1, 2, 3, 4, 5 times 7 is 35, so that means there's 40 electrons, and you can see 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. So it's got 40 electrons. All the F's have 8. The P has to have 10, and that's okay. Here's another example. Let me go ahead and draw this one from scratch. Xenon. So some people are like, wait, xenon's a noble gas. Why does it make a bond? Well, it's big enough, so it's further down on the periodic table. And like I said, some of them can have up to 12 electrons. So if I'm wanting to go through, let's go through and draw this structure. XeF4. Xe has 8, and each fluorine has 7. So 28 plus 8 is 36, so this has 36 electrons. So if I put the xenon, and this one drew it like that, but it's perfectly fine if you want to draw it like this. So I've used up 2, 4, 6, 8, so that gives me 28 electrons. I need to give 6 here, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So to give all the fluorines 8, I needed 24. So now I have 4 left. Where do those 4 go? Fluorine can't have any more, but xenon in the center can have up to 12. And don't put them where you can see the other bonds. Usually what I'll do is put them like on, and they put them on opposite sides. Or if you had put them on the left and bottom right, that's fine too. But make sure they're separate, different from the actual bonds. So I'm going to just kind of touch this up a little bit and make sure that that bond's there, and then these electrons are separate. So we can, like I said, have up to 12 electrons on the center. All right, let's talk real quick about formal charges. So we're pretty good with valence electrons. Every once in a while, there's going to be a funny shaped molecule that you say, well, everybody's got 8, so why aren't they just happy? Sometimes different elements like to have a certain number of electrons, or like to share more electrons than others. And so we can determine this by using something called a formal charge. So a formal charge on an atom in the Lewis structure is the hypothetical charge you would obtain by assuming that bonding electrons are equally shared between bonded atoms, and that these electrons, and that each lone pair belongs completely to one atom. So what we can do, in other words, we can find out if that element is happy the way it is, or if it would prefer to give away more electrons or share more electrons. So sometimes what that can do is help us determine what is the best Lewis structure. And so I'll show you what I mean. So far, none of them we haven't had to worry about it, but sometimes we do. So let's look at how do we find a formal charge. To find a formal charge, we have to take the number of valence electrons assigned to, basically what we're trying to find is how many electrons are assigned to the bottom bonded atom. And to do that, we take half of all the electrons that are bonded. So if you've got a bond, 1 electron goes with each element. And then if you've got an unshared pair, both of those electrons will stay with the atom to which they belong. And so you want to add these together. And then you want to subtract from the number of valence electrons for the free atom. So i.e. where you came up with in the first place, the group number. And then, so you take the number of valence electrons, subtract, take the number of valence electrons for the bonded atom, and subtract that from the valence electrons on the free atom. So it sounds a whole lot more confusing than it really is. So we take the valence electrons on the free atom, and I'm going to do an example in just a second, and it should make sense. Then take half the number of bonds, or half the number of electrons in bonds. Or another way you can do it is just count the number of bonds and use that number. So it's kind of like you don't have to double it and then take half again. But you want half the number of electrons in the bonds, and then the number of lone pairs. So another way to look at it is you use the valence in free, subtract the number of bonds, and then subtract the number of lone electrons. So you need the total of the lone electron. And then it's the sum of all the formal charges should equal the charge on the molecular ion. So I think, again, this is much better done as an example. So let's look at carbon monoxide. Carbon monoxide. So let's see if we can find out what is the formal charge on carbon. So the valence for carbon, for the free carbon, is 4. That's it's in the 4th column. Now, carbon is making 3 bonds, or another way of looking at it is there's 6 electrons in the bonds, and we take half of it. So it may just be easier to take the number of bonds and then subtract the number of the total number of unshared electrons. So that's where I came up with -1. So 4 minus 3 minus 2 is -1. Oxygen, we do the same thing. Now oxygen is a 6th column, so it has a valence of 6, minus 3 bonds, minus 2 unshared pairs gives me a +1. What this is kind of telling me, so if I write the formal charges over it, it's kind of like, remember what I said earlier, that carbon likes to make 4 bonds. So in a way, it's kind of like carbon is one short bond. It's short one bond in this molecule. So that's why it has a formal charge of -1. Oxygen likes to make 2 bonds, so it's kind of got an extra bond, and so that's why it's got a +1. That's kind of what the number means. It's making more bonds than it really wants to, and carbon's making fewer bonds than it really wants to. In this case, there's nothing we can do about it. It's just the formal charges. If I said, what's the formal charge of carbon? It's -1. What's the formal charge of oxygen? Is +1. If we look at the ammonium ion, same deal. Let's look at the nitrogen in the center first. The nitrogen, the free nitrogen, has 5 valence electrons. It is making 4 bonds. So 5 minus 4. It has no unshared pair, so -0. So nitrogen has a +1 formal charge. Each hydrogen, as long as it's making a bond, has a formal charge of 0. But anyway, it's got a valence of 1. They're each making 1 bond. So 1 minus 1 is 0. So all the hydrogen have a 0 formal charge. And so like I said, the total of all the formal charges have to equal the charge of the ion. So in this case, the total formal charges is +1, and the overall charge of the molecule is 1, in this case an ion. It's kind of what this does is kind of says, okay, really that positive charge is based here in the nitrogen. It's the nitrogen that's causing that positive charge and not the hydrogen. So it's kind of a better way of figuring out where the charge is in an atom. And as I was saying earlier, we said nitrogen in the 5th column tends to like to make 3 bonds. So again, it's a +1 because it's kind of making 1 more bond than it normally wants to. And let's just go back over here for a second. The overall carbon monoxide, the overall charge for this molecule is 0. And if we add together the formal charges, we get 0. So the total sum of all the formal charges should equal the charge of the overall molecule. So like I said, formal charges can help us to determine the most likely Lewis structure. And here's some rules to follow. If you can write several Lewis structures, choose the one that has the lowest magnitude of formal charges. In other words, if you add all the formal charges together, whichever one gives you the lowest sum, that's the best structure. If you have 2 proposed Lewis structures that have the same magnitudes, then choose the one where the negative formal charge is on the more electronegative atom. And then, when possible, choose the Lewis structure that does not have any like charges on atoms that are next to each other. So let's look at an example here, and let me, I'm going to see if black works. So I'm going to start with carbon dioxide, and let's just kind of start it out. Oh, let me first figure out my valence electrons. So carbon has 4, oxygen's in the 6th column, so 2 times 6 is 12, so I have a total of 16 electrons. Excuse me. If I have, make 2 bonds, I've used up 4 electrons, so I have 12. And then what I want to do is give each oxygen 6 electrons. The peripheral one, give them enough to have 8. I've used up all my electrons, and clearly this is not my final structure because my carbon doesn't have 8 electrons. So I'm going to have to make a multiple bond. But there may be a couple of choices here. So let's look at this. Okay. So this first structure is possible. So if I take 4 of my electrons from one oxygen and make 2 more bonds with the carbon, everybody has 8, so everybody's happy. if you figure out the formal charges, so oxygen here, this one it's a valence of 6 minus 3 bonds minus 2 electrons, so that's where the positive 1 comes from. This oxygen, valence of 6 minus 1 bond minus 6 electrons, so that's where the negative 1 comes from. Carbon, and let me back up, so oxygen making 1 bond is kind of like, it doesn't like that. Oxygen making 3 bonds, it prefers to make 2 bonds, so that's kind of where this is coming from. Again, carbon, 4 minus 4 minus 0 equals 0. So this structure is reasonable, and you can see that the formal charges add up to 0, which is the overall charge of this molecule. So that's reasonable, but it doesn't give us the lowest formal charges. So if we look at this second structure, you can see oxygen, 6 minus 2 minus 4 is 0. 6 minus 2 minus 4 is 0, and carbon, 4 minus 4 is 0. So this is the best structure here because it gives the lowest number of formal charges, zeros. And when they say magnitude, so this actually, so obviously -1 and +1 add up to 0, which they should, but magnitude means absolute value. So this has a magnitude of 2, this has a magnitude of 0, so this is my better choice. And then even this, if you weren't sure, should I put the oxygen in the center or the carbon in the center, if you try putting the oxygen in the center, you can see that the formal charges are even more out of whack. So even though the total is still 0, the magnitude is 4, and so it prefers this structure. Let's look at another example. So CSN, similar, let's start here. 4 plus 6 plus 5, and then one more for the -1 means that we have 12, 13, again, 16 electrons. And you might say, well, I'm not sure if I should put the S in the middle, the C in the middle. What should I put in the middle? Because maybe I didn't give you good guidance or something like that. And you're wondering, and you say, okay, well, let's try some options. So I've done that. So if I put the S in the center, that's this one over here, you can see that. And then when it came to making double bonds and making sure everybody had 8, you can see that this has actually a magnitude of 5. The total charge should be -1 because it's a -1 ion. So this does have a total charge of -1. If we put the N in the middle, you can see that the formal charges are a little better. So the total magnitude of 3. But here, if you put the C in the middle, then we have a total magnitude of 1. And so what that tells us is that, in fact, the negative charge is based here on the nitrogen, and so it kind of tells us where the negative charge is located, and also gives us the best sharing. So if you're you don't always have to do this, but if you're unsure, this is a really helpful way of using formal charges. So let's do one more, SOCl2. And this is actually very similar to the one we did earlier, where I just told you, oh, make the double bond to O because it likes to make 2 bonds and Cl doesn't. Well, we can kind of use the same ideas here. So if I put the S is 6 plus another 6 plus 14 is 26. So you can see here, if I put the S in the middle and the O, this is actually helping us actually okay, so there is no double bond in this case because the sulfur has the 2 extra electrons. But this one kind of, I'll do that other one in just a second. So this one, if you put the S in the middle, you can see that you have an overall, the S is positive, the O is negative, the Cl's are both 0. If you put the O in the center, we have a similar magnitude of 2, So both of these are actually reasonable, but I'll talk about that in just a second. Here, if we put one of the Cl's in the middle, you can see the magnitude is +2, -1, -1. So that's a magnitude of 4. So this would be the least likely structure. Now, probably out of these two structures, because oxygen is more electronegative, this one would be better because it puts the negative charge on the oxygen. But there's actually one other thing we can do, because we know that some of the elements, as long as they're in the third row or lower down, they can actually have more, that the center can actually have more than 8 electrons. Now, this couldn't happen with the oxygen because the oxygen's in the second row, so we couldn't do this with the oxygen. But because the sulfur's in the third row, we can actually make another double bond. And if we do that, I think I have that picture here, if we make a double bond between the O and the S, we actually have all 0 formal charges, because now sulfur is 6 minus 1, 2, 3, 4 minus 2, so it has a 0 formal charge, and oxygen also has it's the opposite, 6 minus 2 minus 4, so it's 0. So in fact, this is actually probably the most likely structure for this molecule, because of the formal charges, we're able to see that. Now, I will say that if you had drawn this structure here this with the formal charges, I would count that right. If you were to look it up, and this is when we were in COVID, and I knew people were looking things up because they would give me this structure, and I wasn't teaching formal charges then. So anyway, you wouldn't necessarily come up with this, but if you were to look it up, you'd see this structure on the right. I would count this correct. I would also count this correct if you were doing it on a test. Technically, the one on the right is more correct because it has the lowest formal charges. But I'm just introducing it to you so that you'll be aware of it. If you forget about it, that's okay. I had said that I would show you that other one real quick. So we had this structure earlier. Oh no, let me erase that. It was actually OH. Nope, take that back again. Okay, let's start again. It was OCl, and let's see, we got to this structure. This was a few slides ago. And I was out of electrons. This was the first time we introduced the double bond. I was out of electrons, and I said, well, let's take these electrons away from the oxygen and make the double bond, which is what we did. So let's do that. And let's go ahead and figure out the formal charge. So the formal charge of chlorine is a 0 because it's 7 minus 1 minus 6, so it's 0. This one's 0. The oxygen is 0 because it's 6 minus 2 minus 4. And then the carbon is also 0 because it's 4 minus 0. So this is the best structure. And just in case you were wondering, let's go ahead and make a double bond to the chlorine and see what happens if we leave this one. Obviously, this one on the left hasn't changed, so it's still a 0. I'll just put lines to make sure we know it's a 0. And the oxygen here would be 6 minus 1 minus 6, so it's a -1. And this chlorine would be 7 minus 2 minus 4, so it's actually a +1. And so again, this would not be the best answer because it doesn't have the lowest formal charges. So anyway, that would have helped us back then too. One more example. Okay, so one more example. Let's do the formal, let's draw the Lewis structure that best describes the charge distribution in sulfuric acid using the rules of formal charges. So first, let's go ahead and figure our valence electrons. 6 times 4 is 24, so that's a total of 32 electrons. Now this one you might not understand how to, I would probably give you a little help, but that's why we're doing it in the lecture. So sulfur is actually bonded to all 4 oxygens. and then each hydrogen bonded to each oxygen. So you can see here we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So we've used up all 32 electrons, and this is the structure we have. And honestly, I'd be pretty happy with that. And if I gave it to you on a test, I'd probably say that's fine. But if we go ahead and look at formal charges, we can see that they're not all as happy as they can be, and sulfur being in the center can have more than 8 electrons. So if we calculate the formal charge for each atom, the oxygens that have the hydrogens have a formal charge of 0. The oxygens that only are attached to the sulfur have a formal charge of -1. The sulfur in the middle has a formal charge of +2. And of course, H's always have a formal charge of 0 as long as it makes one bond. So you can see here that our magnitude then is 4, because we have a +2 in the center and -1 on 2 of the oxygens. So that means that we're not at our lowest formal charges, and we can actually make some double bonds. So this is what it looks like with the formal charges. The 2 oxygens on the top, let me get a different color here. The 2 oxygens on the top and bottom are -1. The sulfur is a +2. So if we go ahead and make a double bond between each oxygen and a sulfur, we end up with this structure, and then what happens is all the formal charges are 0. And since sulfur is in the middle, it can have up to 12 electrons. So if you were to look up the structure, you would find this with the double bonds. And again, if you gave me this, that would be great. If you forgot and you gave me this structure, that would be okay. But I wanted to put it out there so that you know that that it's important that in real life this is going to be the best structure.